To host the Cryptographers panel, please welcome Honorary Fellow, Gonville and Keyes College, Cambridge, Whitfield Diffie.
Well, good morning. I think I have been on every one of these panels since this conference began, like 32 years ago. And this one is the most exciting I have encountered. I hope you're going to find you agree. They are incredibly opinionated, and they are erudite. They know, I can barely follow them. So I don't know that I'm going to have much further role here except to shut them up when we have to change topics or something like that. But at any event, have a good time. I hope they're always a little slow about bringing them in, but well, yeah. And they'll give me a little cord so I could, Hey, yeah. So, go ahead, sit down, sit down, sit down. To my left immediately is Debbie Taylor Moore. She's a vice president at IBM. I invited her for her expertise in AI. It turns out she knows lots about crypto and other things as well. But she thinks of herself as a public policy person and forced to know all of the things that influence the public policies she wants to talk about. Next, Craig Gentry. Craig Gentry created the greatest jewel in cryptography, I think, since RSA. What's called fully homomorphic encryption, and he is going to be opposed by Tal probably in talking about lots of that stuff. Next we have Tal Rabin. She's a recipient of the RSA Conference Mathematics Award. She was head of the IBM cryptographic group at IBM Watson, which dates back to creation of the data encryption standard. And she is with AWS on leave from the University of Pennsylvania, where she's professor of computer science. And I don't think I need to introduce Adi Shamir. So we're in an interesting position. Remember, this is basically, this is a business conference. And last year we talked a lot about quantum computing and when there's going to be quantum computing and how much of it's going to be and when it'll be a threat to cryptography and things like that. But we're in the great position that NIST and NSA have both decided there is a threat to cryptography, and they have declared we have to implement new standards. So what we talk about this year, the business opportunity, the engineering problems, those are here. And the guidelines and the time schedule make it look as though it's going to go smoothly, but I think Adi can tell us maybe it's not going to go as smoothly.
So I want to share with you a big drama that happened over the last few weeks, and it wasn't covered in the press, so you may not be aware of it. As you know, companies are starting to move away from RSA and from elliptic curve cryptography due to the fact that these crypto systems are vulnerable to Shor's algorithm, which, by the way, was introduced exactly 30 years ago in 1994. And so NIST and the NSA and the US government are all pushing to replace RSA and elliptic curve cryptography by a new kind of crypto system. Most of those crypto systems are based on lattice-based cryptography, and in the hope that they will not be vulnerable to quantum computers. Now, on April 10th, less than a month ago, a paper appeared. It was written by a bright young researcher from Tsinghua University in Beijing. And he claimed that he can solve, on a quantum computer, the problem of finding shortest vectors in a lattice up to some small gap in polynomial time. If this result had held, then it could be the end of the big shift towards a new class of crypto systems. And we would be in the middle of a major disaster. Fortunately, as soon as this paper appeared, and it was 63-page, very dense mathematically paper, the whole community of experts in quantum computing and in lattices jumped into action and started collaborating, exchanging ideas. And about a week later, a very fine mistake was found at the bottom of page 37 out of the 63 pages of the paper. And the jury is still out whether this bug can or cannot be fixed. And in particular, it's not clear what should we do. So the situation on the ground is that that paper, which claimed that it can kill lattice-based cryptography, including fully homomorphic encryption schemes and with some extensions also the NIST proposals, had been saved at the moment. But it was a very close call. So I want to ask the panelists, what do they think we should do in such a situation?
So I'm willing to jump in, but I have to say something about my introduction. Diffie said that it was IBM all the way back to when DES was created. I have to make it clear, I was a child at the time. I didn't manage the team at that time, but...
She headed a group that dated back to DES.
Yeah, at the age of, I don't know what, 8, I ruled the group there. Anyway, but to Adi's question, which is a little more relevant to the thing. So I think what do we do has a few directions that we have to look at. First of all, on the scientific side, I think we have to continue examining maybe new assumptions that we can build things on. And for this specific assumption that was in this paper and maybe was attacked, to keep on trying to attack it, to see maybe we can prove better things about it, sort of to increase our confidence in the assumption. Because assumptions in some way are a social belief system. The longer that they are around, the more faith we have in them, like in the RSA assumption. And we have to get this confidence also in these lattice-based assumptions. But then there's also a practical issue of what do we do now after this thing happened? Are we changing course with respect to implementing things and so on? So neither NIST nor the NSA had said we're moving away from these protocols that we had chosen. And the NSA has a timeline for people who want to interact with national security systems. And if you are a company that is involved in these things, or your customers are, and you need to be able to address these issues, you need to continue with the development and implementation at your end of these quantum systems. Now, I want to say, even TLS, when it was now modified to be post-quantum, they decided to go with a hybrid solution, which means that you will both implement the classical key exchange and you will add a post-quantum key exchange, which is one of the candidates that were chosen in the NIST competition. You combine them in some way and you use it. And I think that the reason I wasn't part of these discussions that TLS decided to go that way is maybe to give a little bit more of buffer time for these post-quantum assumptions to get more street cred in some way. And another thing that relates to quantum in this front is that there are two things that we do most of the time, which is encryption and signatures. And in the quantum world, these things are not the same. Because signatures, if you have a key and it's not post-quantum, once a quantum computer exists, you can revoke the key and it won't be used anymore. Encryption is slightly different because encryption, you can store encrypted messages today. And when the quantum computer comes in later, you can decrypt them. So when you're thinking about your post-quantum strategy, you also have to take these 2 points into account, what you do with encryption versus what you do with signatures. So this is sort of my thinking on these things.
A general broad distinction between authentication and confidentiality
Yes.
in security systems is that usually authentication systems don't have the same time sensitivity because
Just-
you can't collect traffic now and wait to exploit it later.
I just want to mention that everything that happened over the last 3 weeks is peer review at its very best. Because usually when somebody publishes a mathematical paper, and it may take months or years before a potential problem is pointed out by the peers. So peer review has many problems, but in this case, it worked exactly as it should have been, and we reached a quick conclusion after about 1 week when Thomas Vidic from the Weizmann Institute and Hongxun Wu from Berkeley had pointed out independently the problem.
I can take a slightly contrarian view. I mean, a month ago, we didn't have a quantum attack on lattice-based crypto systems, and we don't today. So I think not much has changed. If you didn't know before that most cryptography is based on assumptions, that certain problems are hard, well, you know now, and that's the way it's always been. That's why they say that cryptographers seldom sleep at night. So, and if you knew how many times I personally have thought that I've solved the P versus NP problem, like, proven that P equals NP and that you can break all crypto systems, you'd be shocked if you took that seriously. So I don't want to minimize, Yulei Chen's contribution because it was a serious paper and it kept people up at night for 8 days, and it was a serious attempt. But I would say that we're back to the status quo, and we should proceed with the post-quantum secure crypto systems that NIST has standardized.
I agree with you that we should continue with the systems. As I had said, you should go and do whatever. But I'm not 100% sure that we're exactly at the same place, because I think that a paper like this that lasted for 8 days puts fire underneath people. And now I'm sure that more people are working to try and attack. I even know some people personally. And I do think that it has shifted a little bit. I think that people were quite not fierce enough against the quantum.
Let's hear what Debbie had. I think you wanted to poke in.
Yeah, absolutely. So I'm thinking that I share a lot of the ideas that everyone's brought up on this topic so far, but I also think that NIST is a great convener, and this is one of the most crowdsourced efforts that we've seen in our time in terms of all of the input that has gone into it. And as Adi said about the process working as it should, I think it's really important that we not panic, but we're happy that folks are challenging these algorithms that are moving toward being standards. And so I think that the put the foot on the gas piece of it is where we really are operationally. If you are looking at a post-quantum cryptographic migration plan, you can expect that when NIST releases the standard at the end of summer, that there's going to be a tremendous amount of press, a tremendous amount of pressure at the C-suite level to understand what your plan is as an organization. And I think just overall that when it comes to visibility into crypto inventory or crypto systems within enterprises, if you're a security person working in these enterprises, that having a good view on that operationally is never going to be something that you wouldn't pursue. So it's definitely a go forward.
So I gave a talk in Charleston, South Carolina, a couple of months back, and somebody got up and said, "Why shouldn't we panic? You're talking about not getting this done till 2035, and it was a special, secret stuff conference. We have things that are classified for 30 years. If we are doing it today, then the stuff we've had in the last few years would still be vulnerable before its classification expires." And so I think there may be some truth to that. I don't think there's any good in panicking, but I don't know. Don't find a lot of confidence in this.
I think when you think about what's happened in the past is sort of prologue. You think of the idea that we've had many schemes be deprecated, and it takes a pretty long time for us to actually sort of rid ourselves of them. And that process in and of itself, it becomes really complex because computing's so much more complex than it was, you know, in 2004 or 2011 when MD5 and SHA-1 were deprecated. Now you've got a lot of third-party risk management to consider because you have dependencies on a lot of folks that you don't have control over exactly how they're applying their plan toward this effort. And so starting early may give you an opportunity to be ahead of the game.
Yeah, okay.
I
I
think
mean, I think
I'm
there's no
on-
question. We need to work as fast as we can. It's just not clear to me we haven't already run over.
I think I'm on record saying that if you have secrets which should be kept for 10 years, then use RSA, use elliptic curves. It doesn't matter. There won't be quantum computers capable enough before then. If you have secrets which you want to protect for 100 years, don't use any public key crypto system, not the new generation or the old generation. Just use secret key cryptography, and that's it.
Okay.
So I was looking at techniques like that, of course, to try and see what we can do. So I saw these things of people moving around with cars, bringing one-time pads from one place to another.
Attaché case.
Yes, but these things are attackable as well. I mean, you can attack the people driving in the car.
I know, but
and,
I have no confidence in any public key crypto system
Yes, yes, of course.
to remain secure
I agree.
100 years from now.
So,
I
I mean,
agree.
that turns into a recommendation, which is public key seems to be needed for something the size of the internet. But a lot of things like banking systems, military systems, are a lot smaller than that, and you can do them with classic symmetric key management, and that is probably the prudent thing to do.
I want to say more than what you're saying even. People are talking, we want to switch to post-quantum and so on because our stuff needs to be secure for so long. And then they use RSA with 512-bit key, right? So you think, what are they doing? And not only just RSA with 512 bits, they're doing a lot of other things which are very insecure, but they're going to be post-quantum. So they don't really think about their whole security model as a whole and all its components.
Okay. So the flavor of the year, exciting as quantum is artificial intelligence. And artificial intelligence is a little like the Porsche 911, right? They've kept that model name for longer than any other that's been around, but they kept changing the car. And the model name AI has been around since the mid-50s, and they keep diddling it. Give us an update on the impact of AI on security today, because it has a lot of.
Yeah, I would definitely agree with you. They often talk about black swan events and the idea of something happening that's so unusual, but so impactful, and that we somewhat anticipated it, but not to the extent that it actually impacts us. And I really look at the pandemic and also the introduction of generative AI in 2022 as sort of those sorts of events that sort of take us a little bit off our game. I think that overall, what we're seeing is that what we saw in the beginning was a little bit of panic as AI went straight into the hands of end users and folks that are, maybe not traditionally the folks that are managing these things. And for security professionals, all of a sudden, in the beginning, you have one job to do, right? But then you have three jobs to do. You have to secure your own organization's AI implementations and make sure that the company stays out of harm, and also that it's not harming its customers. You have to be concerned with how you're using AI in order to optimize operations from a security standpoint. And then the third thing is understanding what the power is of generative AI, in that you have to be concerned about its weaponization against your organization. And so these are new responsibilities that involve really working with very smart people like this who are spending time around developing the algorithms and spending time around really understanding beyond the infrastructure layer we're used to protecting, looking at data, looking at analytics, looking at the intent of data models. And as security people, we found ourselves sort of pulled into these discussions in a way that maybe wasn't so comfortable, but is becoming more and more our role, because we're sort of the folks that are most engaged in a risk management framework, and it all sort of comes back to the security folks.
Yeah, I think this conference is sort of a call to arms to protect our privacy and to develop a safe AI ecosystem that we can live with. I mean, I think we have maybe a limited time window. And there are things we can do. I mean, for example, zero-knowledge proofs, you can prove that an AI model was trained in a certain way, that it was trained without trapdoors, that it was trained in a differentially private way, that doesn't reveal the individual records that it was trained on. You can do these sorts of things, and you can create, kind of a supply chain for AI models and data. And that would be really great, that you'd have this whole ecosystem that's actually safe. Of course, it's going to be like sort of a dark net of neural networks, that's going to sort of exist off to the side. That, it's a bunch of models that you don't know anything about where they came from, and people use them at their own risk. But for the main sort of batch of AI models, I think we have sort of a chance here as security professionals or whatever you want to call yourselves, to actually make this safe.
I want to mention that the area of AI security is a completely new area of research, which was barely touched until a few years ago, and it raises completely different issues. For example, one of the biggest trends at the moment is that big companies are spending billions of dollars on training large models, and they keep them proprietary, so all the weights in those networks are kept secret, but they allow people to interact with this black box by giving them input and observing, getting the output of the network. And one of the interesting questions is it secure? Is this practice secure? Or can you recover the internal parameters of a deep neural network that so much money had been spent on training just by interacting in polynomial amount of time? So later this month, I'm going to present a paper at Eurocrypt where we show that there is indeed a polynomial time algorithm which allow you to find all the weights of a network by asking polynomially many queries, polynomial in the number of neurons, and getting the polynomially many answers. So it's very dangerous, actually, to allow people to interact with your model unless you take extra precautions.
Well, this seems like one of these many examples of, they deserve what they get. I mean, the owners of the original data are claiming, oh, no, you need to license it from us. And these people say, no, our people have a right to read your books. Our devices have a right to read your books. And now those people who compile the models want to say to their users, oh, no, you don't have a right to know how our system works. You have to pay us to use it for you. So, now, everybody wants everything. But it seems to me that there are two distinct sorts of AI security problem. Well, one is you can dream up, well, no, maybe three. I mean, one is the one that's represented so clearly by the, quote, hallucinations of the AIs, right? I ask who the crew, who the nurses were in Operation Petticoat a few days ago, and it said Jamie Lee Curtis, who was daughter of one of the officers in the movie, but she was 2 years old when the movie was made. She wasn't playing one of the nurses, but that kind of thing. But the second, even if you can get them, I use one called Perplexity that shows you what the sources are. So with a bit of work, you can go and you can get a notion from more classical techniques. But the two big questions, I mean, one is, all right, how do you guarantee that people can't twiddle the AI? That's what you'd mean by security. People twiddle it somehow so that it gives answers that please them. But the other issue is, how can AI be used as a penetration tool? And it strikes me it's going to produce a revolution in operational intelligence, because it can process a lot of low-grade ore and come up with things that people didn't want to reveal, but you get intelligence that is very robust, because very, very hard to conceal every one of your little activities that points back to what you didn't want to reveal.
So I want to say one thing in relation to the hallucinations and how AI can be used in security. So AI, of course, can be used to help you set up systems and so on. But on that front, I think we have to be very careful. I don't think that we can build a system that will be the front to the customers, that will give them answers. But it could be a great tool to have aided assistance for setting up systems and so on. And of course, because of the hallucinations, it's very dangerous, because if it tells you to misconfigure a key, it doesn't matter that it was one hallucination. It's a devastating problem. So in that respect, I think it could help, but we should not rely on it fully. I think there is still issues with AI on that front. And I want to touch upon one more point, which is this issue of tampering with the data, but another aspect of it, systems learn on inputs of people, and in Europe, for example, there's the GDPR, which has the right to be forgotten. So I'm a person, and a model has been trained on my data, but now I don't want that model to be based on my information at all. And the question is, how does the system unlearn this data? Can it be done at all? So there are all kinds of budding research now on this front trying to do it, that maybe you train on small systems, and then if my data is in this little portion, that whole portion is retrained again. But this is definitely an area where there's room for a lot of innovation. So as Craig said, a call to arms. So a call to arms on this front as well, to try and see what we can do.
So
There's a lot of keeping the small people in line here. I mean, the right to be forgotten isn't the right to be forgotten by the secret police or the tax authorities or your creditors. It's the right not to have, random individuals who didn't keep records be able to find you in the search engines. And similarly, the wanting, restricting the way people can use the AIs so they can't learn to make bombs or commit suicide or things like that. This is keeping the small people in line stuff.
You raised an issue, but it's much broader. Where are we going to get all the data for training large language models or models designed to solve particular problems? And the practice had been that you just take the whole internet, everything which is accessible on the internet, and use it as training data. And this raises very thorny issues about who owns the copyright to stories which appear on the internet. You know that New York Times was suing OpenAI for using their stories to train. And in my opinion, this can be the most important determinant factor who is going to win the AI race. Because in Europe, for example, they are extremely strict about getting permission to use data. And it's almost impossible, if you think about it, taking any piece of training data and looking who is the legal owner of that piece of data and getting a written permission to use it, etc. So I'm quite pessimistic about the possibility of legally developing large language models in Europe unless you break the law. In the US,
Hollywood, they have this, scheme for finding actors who played in something 50 years ago and finding out who has the rights.
No, but the point I'm going to make is that the US will have very soon to decide whether you are allowed to use the whole internet and data which is potentially copyrighted in order to train on. And in China, I don't think they have any legal restrictions. So the government will probably give the big Chinese companies all the data they need in order to train the large models. And therefore, it might be that the Chinese will eventually win this race just due to the lack of legal constraints.
And what intelligence, what databases are the intelligence organizations using?
So I was just going to say, I think practically speaking, from a security operations standpoint and from organizational standpoint, people really need to have governance. They need to know where their AI is, who has access to it, how it's being used, and they need to establish little councils within their organization that when they produce AI solutions, and that means looking back at the ones that are already out there, there's some 74%
There's a
of
cultural
folks.
divide. You come from Washington, where they believe in the government. This is the northern tip of the valley, where they don't.
Well, I think in any case, though, having some control over it will keep you out of court, and having some visibility around it will as well.
I mean, that raises an interesting question about how we educate government officials about such a complex issue in a
I think that's
in a
Debbie's
realistic.
job.
Yeah.
Well,
That's your job. So I mean, if they can't even get end-to-end encryption right, then that's pretty worrisome, right? On the other hand, you have NIST, which is deals with very complex issues like post-quantum crypto. So obviously government is not monolithic, but it's must be a challenge to try to explain all these issues in a way that's
Well,
will
give you
lead
a
to
chance
realistic
explain
solutions.
something else. So I was saying that I thought that fully homomorphic encryption was the greatest gem since, at least since RSA. And those of you not familiar with it, it's the notion that I don't trust some central computer. And I want it to solve a problem for me, but I don't want it to know what the problem is. And I can encrypt the problem and send it to the central computer, and it can compute on this encrypted stuff and eventually send me back the answer without ever understanding any of it. So I want an update. This is one part of an area called multi-party computation, where parties that don't trust each other are doing parts of computations and interacting. So I was hoping that Craig and Tal would give us an update on how all of that is going.
Start.
Okay, I'll start. So first of all, just to say what these areas are, this umbrella of multi-party computation, threshold cryptography, fully homomorphic encryption, they each have different flavors. And Craig will talk about fully homomorphic encryption. But the idea with multi-party computation and threshold and FHE is that we want to do two things possibly. One, to increase the security in the system, and the other one is to do some privacy-preserving computations. When I say that we want to increase the security of the system, I'll give you a very small example, which is very related to Adi, who's sitting here on my left. And you have a key in your system, which is a very important key. Let's say it generates signatures. Maybe you're a certification authority. And that key, if you put it on your server somewhere, is a single point of failure. There could be a malicious attack on it, but even an inadvertent thing could happen. Somebody comes to serve the machine and by mistake dumps the whole memory and the key is exposed. This is a big issue. So how do we improve the security of these systems with a very simple technique? Let's say that the key is the number 11. So we take the key and we break it into two numbers, a 7 and a 4. That add up to 11. You put a 7 on one machine, you put the 4 on a different machine, and you can see that immediately you've enhanced the security of the system, because now in order to expose the 11, you need a fault to happen both here and both there. The reason I'm saying it's connected to Adi, it's connected to a technique called secret sharing, which Adi invented. And this technique already improves our security. But now you might tell me, but how do I sign when there's a 7 here and a 4 there? But I will rest assured, we can do it. We can take from these two pieces without bringing them back together and generate a signature. And through similar techniques, but more involved, we can also do privacy-preserving computations. And just as an example of what such a problem would be, you have a hospital, two hospitals, and they each have information about a very rare disease. But due to HIPAA regulation, they cannot share this information. But we do want the utility that we can get from research that shares data more expansively. So these techniques of MPC can help you do these things as well. So these are sort of the techniques that we're discussing. And Craig will talk a little bit about FHE, which really, as Whit said, is a crown jewel of these things, and tell us how to do, and then we'll continue.
Okay, sure. Yeah, yeah. So FHE. Yeah, I don't know how much you guys know about FHE, but I'll just since nobody seems to understand me a lot of the time, I'll start with my analogy for FHE. So basically. So like Whit said, basically the idea is you can encrypt your data, you can send it somewhere else. They can do computation on encrypted data, send an encrypted result back to you, and then you can decrypt it. So it's kind of like it's in a box, you know, and you just send this box over, and they do the computation while it's over there, right? So the analogy I often use is kind of silly. So Alice, you know, has this jewelry store, right? And she, you know, she gets raw materials like gold, diamond, and silver. And she has these workers, and you know, the job of the workers is to convert them into nice, you know, finished pieces like necklaces and rings and stuff. But she's, you know, kind of paranoid, so she doesn't really trust her workers, right? So she wants her workers to put these pieces together without actually having access to the raw materials so that they can steal them or whatever. So her solution is that she has this this locked box with gloves in it, you know, kind of like, you know, when you're dealing with the biological materials. So she has this locked glove box. She has the key. She can stick the raw materials inside, along with, you know, soldering irons or whatever they use to make rings and stuff. And you know, she can and then when she can give that off to the workers, and the worker can stick his hands inside and sort of make the piece while it's inside the box. And you know, he doesn't have the key, so he just sends it back to Alice, who decrypts and recovers the final result. So FHE is kind of a mathematical equivalent of that analogy.
You know, this never stopped thieves from grabbing the whole box from the jewelry store and walking out.
It's an impenetrable box. That's the assumption. That's kind of like a cryptographic assumption. So you see the weakness there. Okay, so that's FHE.
How are we doing on speed these days?
Yeah. So that's the thing. So you know, you can imagine just like you know, having the workers sort of manipulate the pieces while it's inside the box is kind of cumbersome and maybe slows the workers down considerably. That's also the case for FHE, that basically when you encrypt, say, a bit into this giant ciphertext, and then you know have the server manipulating these giant ciphertexts instead of the natural bits, there's a lot of overhead. So from what I understand, the overhead is down certainly a lot from when I came up with the first scheme. The first scheme was like the overhead was, you know, an incalculable number because, you know, we couldn't even implement that basically. So it was definitely over $1 trillion. So and now it's around 10,000, I think. So that's a lot of improvement. Certainly, there's been a lot of work in the cryptographic community to get that number down. 10,000 is still a lot, so you know you can't run LLMs privately using FHE, but you can run smaller models in reasonable amount of time.
So the government also strongly believes in this thing, and it put a program in place, a DARPA program, to try and develop hardware to accelerate these operations. And in fact, this project is currently running, and we're expected to see some prototypes soon that will make these things faster. But I want to say about these techniques in general. Multi-party computation and FHE have been designed over the past 30, 40 years, and we really believe in them in ways of improving security and enhancing privacy. But somehow, it hasn't taken off over all these years, despite our great belief in it. And the question is currently whether legislation, in fact, will force us to need to use these things, because if we won't be able to share information, these techniques will enable us to compute over the data, even if it's in distributed or secret form. So hopefully, maybe now is the time, which will be the golden age for these types of techniques.
Well, you're not my view for a while has been that FHE is wonderful for certain particular problems. The famous one is called the private search problem. You know, Homeland Security was looking for a terrorist in Vegas and says to the hotels, give me all your logs. We want to know who's in Vegas. I don't know, what, happens in Vegas stays in Vegas. We won't tell you that stuff. Tell us what the characteristics of a terrorist are, and we'll look for them for you. Oh, no, we can't tell you that. That's secret, etc. So these are ways of having two mutually distrustful parties do things. Drew Dean had a project a few years ago at DARPA that did another kind of specialized thing for which FHE is wonderful, which is having what's called a black conference bridge. You want to have secure phones talking, a bunch of people talking, but the center that mixes the voices, you don't want to have to trust it. And he managed to do that using iPhone 5s and Amazon Web Services. But it seems very far out to think, well, we're just going to go, we're not going to buy a bigger computer. We want to do this huge job, and we're doing it entirely security. We're going to do it by hiring remote computing facilities.
I think,
Go ahead, Debbie.
I was just going to say, I think just the general public is really moving very quickly toward end-to-end encryption on their own. And I think that there's a lot of work that's being done from a legislative standpoint since the expiration of the Patriot Act, and the fact that you look at the uptick in use of certain end-to-end encryption messaging applications, you look at what social media platforms are doing and making very big strides toward offering this capability to end users. And it's a lot easier for those platforms to be able to give you back some privacy as opposed to spending so much money on thousands and thousands of moderators that have to manage content or make decisions about content. So there's a lot of general use that's happening.
I want to strengthen your point about that FHE is great for some application. I want to say none of these solutions, not the Threshold Crypto, nor MPC, nor FHE, can be used broadly. You really have to check what is the specific thing that you need to do, because all these solutions have a cost associated with them, and you really need to check the trade-offs. Nothing is a solution for everything. So I agree 100%. Maybe in some cases FHE, in some cases MPC. All depends also what your setting is.
So another sort of issue. Back some years ago, somebody wrote a book about the communes of the 60s, and said, they worked fine with honest, energetic people, but they fail utterly against deceitful grifters who wedge their way in. And we have a similar problem today, I think, in open source computing, because something called the XZ bug was found in things provided by open source, and it was a very subtle trick. Some ways analogous to something NSA tried 10 years or so ago with the double elliptic curve random number generator. So Adi, what?
So this is a wonderful example of the dangers of open source software. Apparently, there was a compression package, doesn't seem to have much to do with security, and it was maintained by some guy who was not paying too much attention and not doing a big effort to maintain this package. But this package found its way to zillions of systems. Basically, it was used in all the Linux systems around the world. And apparently, some Chinese operatives muscled in and claimed that the guy who was maintaining this open source software was not doing a good job, and they offered to help. And they actually introduced a subtle bug into the software. And within a few weeks, it would have found the new version of the ZX software, the XZ software, would have found its way into millions of Linux computers. And this disaster was again averted at the very last moment when the original maintainer of the package noticed some small timing differences in the performance of this software, and he wondered, why is it a bit slower than it should be? And he investigated, and he caught it on time. But if he hadn't looked at the software in the new version, which was kind of proposed by the hackers,
Shades
Really
of
disaster.
Cliff Stoll 40 years ago in the 35-cent era in the accounting routine.
But here I want to add something. Open source is changing its face. In the past, open source only dealt with software. Today, it is increasingly common to have open source deep neural networks for doing all kinds of computations, classifiers and large language models, etc. And some companies or individuals who are developing such systems are developing all the parameters by training and then putting it up for everyone to use. And the problem is that whereas open source software at least had the advantage that multiple people had the chance to look at the software, and some of them might have discovered that there is a bug in it. If there is out there an open source deep neural network, how are you going to look at the billion parameters, just billion numbers, and tell that there is something wrong and that there is a backdoor there? It is the idea of having multiple eyeballs looking at the data become mute.
Well, as we're coming to an end, I think I'll talk about some other ends. We lost 3 remarkable people in this community this year. The first is David Kahn, who wrote the book The Code Breakers in 1967, which was my inspiration, and I think that of a variety of other people. It gave, in many ways, about many things, still the best, most insightful discussion of cryptography and cryptanalysis in the signals intelligence world that has ever been published. And shortly after David died, the 2 grandfathers, godfathers of British security died. The first is Fred Piper, less well known. But if you look at British security, his graduate students and their children and so forth are everywhere. And he formed a Masters of Information Security program at Royal Holloway that trained a whole bunch of people that are CSOs and such all around Britain. About 3 weeks after he died, and much more a surprise, much younger, Ross Anderson died. And Ross Anderson, very well known for a textbook in security engineering and for his very insightful and abrasive comments about a million things. And I imagine he died of a heart attack, but he's one of third of my friends to, have a nap and have his wife find it, go look for him for dinner and find that he died. At any event, to avoid, somebody said, you really shouldn't end on a down note like that. So let me give you a more up note. There was a birth in the world today. Now, this is a funny birth announcement because we don't know the sex of the baby or the length of the baby or the weight of the baby, but we know what the baby is going to do. And this baby is going to break RSA. But it's not going to do it by quantum techniques. After all, RSA is a really big problem. It's going to use general relativity. You heard it first here. Thank you all very much.